My name is Shivani. Today I am going to present my project titled Smart EV Dashboard with ADAS using STM32 and Python dashboard. This project focuses on improving vehicle safety by detecting nearby obstacles and providing real-time warnings to the driver. Electric vehicles are becoming more popular and driver safety is an important aspect of modern transportation. Advanced Driver Assistance System or ADAS help reduce accidents by alerting drivers about nearby obstacles. The main objective of my project is to detect obstacles using ultrasonic sensors, process the data with an STM32 microcontroller, display the information on a Python dashboard, and provide warning indications through LED and a buzzer. The main components used in this project are STM32 Blue Pill microcontroller, 3 ultrasonic sensors, LED, a buzzer, and UART communication, and a Python dashboard running on a computer. The STM32 acts as a controller, the ultrasonic sensor measures the obstacle distances, and the Python dashboard displays the sensor data in the real time. This block diagram shows the working of the system. The 3 ultrasonic sensors continuously detect obstacles and send the measurements to the STM32 microcontroller. The STM32 calculates the distances and applies the ADAS warning logic. The processed data is then transmitted to the Python dashboard through UART protocol. Based on the measured distance, the LEDs and the buzzer provide warning indications to the driver. Working principle. The ultrasonic sensors work by transmitting an ultrasonic pulse and receiving the reflected echo from an obstacle. Using the echo time, the STM32 calculates the distance. These values are sent to Python dashboard through UART communication. Depending on the measured distance, the system classifies the obstacle as safe, caution, or danger and activates the fault alarm. The software flow. The software first initializes the STM32 peripherals including GPIO, timers, UART, and the ultrasonic sensors. The controller then reads the distance from all the 3 sensors one by one. After calculating the distances, it sends the values through UART protocol to the Python dashboard. The dashboard updates the readings and the warning logic checks the threshold values before repeating the process continuously. Python dashboard and the live results. This slide shows the Python dashboard developed for the project. It displays live distance values from all 3 ultrasonic sensors along with the obstacle. For example, if the left sensor detects an object at 25 centimeters, it is classified as danger. A distance of 70 centimeters is shown as caution, while the 110 centimeters is considered as safe. The dashboard updates continuously as the new sensor readings are received. Advantages. The advantages of this project include low cost, real-time application, reliable and scalable, and which has future scopes. In the future, the project can be enhanced by adding the TFT display, Bluetooth, Wi-Fi connectivity, and GPS tracker. To conclude, this project successfully demonstrates a low-cost ADAS prototype using STM32 microcontroller and 3 ultrasonic sensors. It measures obstacle distances accurately and sends the data to a Python dashboard using UART. It provides real-time warnings using LEDs and a buzzer. This project can serve as a foundation for more advanced driver assistance systems in future electronic vehicles. Thank you for your attention. STM32 Cube ID. The main controller used in this project is the STM32 Blue Pill based on the STM32F103C8T6 microcontroller. It receives the data from 3 ultrasonic sensors, calculates the obstacle distance, and executes the ADAS warning logic. The STM32 is programmed using STM32 Cube IDE in Embedded C. It uses GPIO pins, that is general purpose input output pins, to interface with the sensors. It The timers are used to accurate the pulse measurement and the UART communication to send the processed data to the Python dashboard in the real time. It also acts as the brain of the entire system. The main code consisting of four parts: the initialization, sensor reading, ADAS warning logic, and UART communication. The initialization part consisting of all required peripherals such as GPIO, UART, timers, and the ultrasonic sensors. It also prepares the STM32 microcontroller so that all the hardware components are ready before the program starts. It also does the sensor reading. The sensor continuously reads the distance from the three HCSR04 ultrasonic sensors. It also warns the ADAS system. The measured distance are compared with the predefined threshold values. Depending on the distance, the system classifies the obstacle as safe, caution, or danger. And finally, the UART communication. The STM32 sends the calculated distance values to the PC using UART serial communication. System and peripheral initialization. It initializes the STM32 and configure all peripherals including GPIO, ADC, UART, and timers. The timers are then started to generate periodic events used for real-time EV control and sensor updates. The line 102 represents software module initialization. It initializes the EV module, ultrasonic sensors, ADAS module, fault detection, and UART shell. The battery state of charge is also initialized using ADC reading. The flag EV representation, also known as the main control loop. In the it while loop is the main execution loop. The program continuously reads accelerator and brake inputs. It updates the vehicle parameters, measures obstacle distances, execute ADAS logic, detects faults, and without stopping the main program. This part of the code prepare and transmit real-time vehicle data through UART that includes speed, SOC, torque, motor temperature, obstacle distance, TTC, that is time to collision, ADAS warnings, and fault status, which are displayed on the Python dashboard. This part of the code reads accelerator, brake, battery temperature, and ultrasonic values. Here, here the code calculates vehicle speed, battery level, motor temperature, and updates EV parameters. It also calls the ADAS logic to calculate forward distance, backward distance, collision warning, blind spot detection, and time to collision. This part of the code controls the LED on-off based on ADAS warning levels. Sonic sensor module ultrasonic.c. This module interfaces with three ultrasonic sensors placed at the front, left, and right. It sends a 10 microsecond trigger pulse, measures the echo time using timer 2, and calculates obstacle distance in centimeters. The measured distances are stored and made available to the ADAS module for real-time obstacle distance. In ADAS.c, the ADAS module reads the ultrasonic sensor distances and calculates the time to collision based on the vehicle speed. It detects forward collision risk, blind spot detection, and overspeed conditions using predefined thresholds. Fault.c. This module continuously monitors critical vehicle conditions such as motor overheating, low battery state, and severe collision warnings. If any fault is detected, the vehicle enters into the fault mode and a yellow fault LED is switched on. When the fault is cleared, the system resets important parameters and returns the vehicle to a safe parked state. In ADAS.h, header file. This header file defines all ADAS thresholds including collision distance thresholds, blind spot distance, overspeed limit, and TTC values. It also defines ADAS data structures, alarm levels, and function prototypes used by the ADAS module. In fault.h, this file defines the different fault types such as fault none, fault OT, fault SOC, fault collision. It also declares the fault management structure used to initialize and detect structure and functions to initialize, detect, and clear faults. In EV controller header file, the EV parameters such as accelerator, pedal, brake pedal, speed, motor torque, battery, power, vehicle range are defined. It also specifies the vehicle speed limit, maximum motor temperature, and battery capacity. The project was developed in STM32 Cube IDE and compiled into the ELF file, which was loaded in the PICSimLab. The STM32 Blue Pill simulation. Virtual potentiometers simulate the acceleration pedal, brake pedal, SOC, and the motor temperature, while the three ultrasonic sensors simulated obstacle detection at the front, left, and right. Timer interrupts periodically, which updates the EV model and the ADAS algorithms. The STM32 transmitted real-time vehicle parameters such as speed, battery, SOC, motor temperature, range, and warning status through UART. Uh, when the accelerator pedal is pressed more, the motor produced higher torque, causing the whole vehicle to accelerate. As more power is drawn from the battery, SOC, and the estimated range decreases. When the brake is increased and acceleration is decreased, motor torque also decreases. We observe that the torque is negative. When the torque is negative, the vehicle slows down and TTC, which is time to collision, increases if such that it is moving from away from the danger. When the speed increases, when the speed increases, battery drains faster. That means the range will decrease. High speed means the vehicle covers more distance in less time. Battery SOC. When SOC increases, it estimates the range. When the SOC decreases, the range decreases. Motor temperature. When the motor temperature increases, the vehicle gets heated up more easily, so that the motor temperature should be as low as possible. Front distance. When the front distance decreases, the red LED will be switched on. Yellow LED will be also be switched on. Yellow LED will be yellow LED represents the fault. When the acceleration pedal increases, the vehicle speed and motor torque increases, while the battery SOC and driving range decreases. When the brake pedal is applied, which applied is increased, the vehicle speed decreases, reducing the motor torque and slowing or stopping the vehicle. In the EV dashboard, when the accelerator pedal is increased, the motor receives more power, so vehicle speed increases. More torque increases to provide acceleration. SOC decreases faster because more energy is consumed. When acceleration pedal is decreased, and brake pedal increases, we notice that less power is applied to the motor. The braking force increases, causing the vehicle speed to decrease. When the acceleration pedal increases, the vehicle speed and motor torque increases, while the battery SOC and driving range decreases. When the brake pedal is applied, which applied is increased, the vehicle speed decreases, reducing the motor torque and slowing or stopping the vehicle. And embedded systems development using STM32, I learned sensor interfacing, timer, GPIO configuration, UART communication, ADAS algorithm implementation, and fault handling. I also learned to simulate the complete system in PICSimLab and display real-time vehicle data on a Python dashboard, improving my coding, debugging, and system integration skills. Thank you for your time and attention. This project has strengthened my understanding of embedded systems and automotive electronics, and I look forward to apply these skills to more advanced real-time EV and ADAS projects.